Hey guys, my name is Stephen Liu. Today I'm going to be talking to you about my implementation of the inverse kinematic solver. It's a solution using the pseudo inverse of the Jacobian. So before I get started, I just want to thank a few people. I want to thank Rick Parent. He is the author of Computer Animation Algorithm and Techniques. I used a lot of the implementations that he has in his book and a lot of the equations that he explains. So I'd like to thank him for this book. It's really, really useful. I definitely recommend this book if you're interested in computer animation at all. I also want to thank Alexandros Dermanakis for giving me some personal help with the implementation of the inverse kinematics with his OpenGL example. So I'm going to go ahead and get started. So with our initial problem, say we're given some sort of joint set. It can be, say, a robotic arm. It can be some sort of arm in general with a lot of different joints, with multiple joints in general. And we have some position E, which is the end effector. Something we need to do is we need to reach that goal position G. So say we're given this position of E, and we need to reach this. So say it's some object that we need to reach with the robotic arm, or it's some sort of just position that we need to get to. One initial thing is we can, with the position of E going to G, we need to solve for all the local angles of each joint. So we need to solve how these joints are going to move and turn in order to reach that goal position G. One problem that we find here is that each angle can have multiple solutions to it. So say, for instance, our E reaches that G, our P2 can have multiple angles to reach that G, or our P1 according to, you know, how that E is going to reach G. And one thing that we're looking to optimize is we're looking to try to find something that's the most natural. So if this is a robotic arm or a human arm in general, we want it to look as natural looking as possible without having any sort of weird effects. So initially, say we are given some sort of independent variables y, and we need to, we're given some input variables x. Say, for instance, that each x is a velocity that maps to y. So we can think of this as an equation y equals f of x. One thing that we can do in order to basically calculate how each input is going to affect the output is to take the partial derivative. So if we take the partial derivative and run the chain rule on this, we can give this partial derivative of y is equal to the partial derivative of x. And so this is going to be our first start to getting the Jacobian. If you look right here, we have some v, which is going to be our velocity, is equal to the matrix of our Jacobian. So this is going to be what our Jacobian is, and we're going to be given some sort of theta, which is our angles of the joints. So that is going to be a vector of all our joint angles. And this is going to be the equation right here that we're using to compute each of the angles. So one issue that we do run into is normally in this case, with our v equal to j theta, we can take the inverse of j and bring that over to the other side, and therefore we can get all our thetas is equal to the j inverse times v. One problem though is our j, we may not be able to take the inverse of our j. There may be cases in our Jacobian that we cannot take the inverse, and that's going to cause some problems. So one thing that we can do is we can take the pseudo inverse approach. So with our pseudo, actually let me go back and kind of explain what the Jacobian is. So our Jacobian J is basically just a matrix, and it's going to relate how the function of the current, it's going to relate the function of our current pose with the next pose. So that's what our Jacobian is. So going back to this, to take the pseudo inverse, as you can see, we take the transpose of J, which is our Jacobian again, and therefore we can take the inverse of J transpose J to each side, and this will allow us to bring our J to the other side. And as you can see, that J plus is the pseudo inverse of our Jacobian, which is J transpose J inversed times J transpose. So that is our pseudo inverse of the Jacobian, and that's going to allow us to bring that J to the other side and calculate the angles of each of the joints. So let me go ahead and just show you my implementation of the pseudo inverse of the Jacobian using these. So say for instance, this is our joint set that we have. So I have 3 joints right here. So I have our initial base joint, have a couple of joints right here, and then I have this little end effector. And using my mouse cursor, I can go ahead and create a goal for this joint to reach. So if I say, for instance, press right here, then my joint's going to my end effector is going to reach that goal. And using the pseudo inverse, I can calculate each of these joint angles to correctly rotate. As you can see, it works semi-decently. It's definitely not bad at all. Naturalness. I do not have any angle constraints on here, which may be an issue. One reason I did not use angle constraints in my implementation is when I was using it, it did constrain it a little too much based on my angles, which caused a little bit of difficulty reaching that goal based on the angles of each of the joints. So as you can see, overall, it's definitely not a bad implementation. One issue you will see though with the pseudo inverse is just that popping right there. So what happens is if it finds a spot that is unreachable for the joint, it's gonna run into some popping. But as you can see, when I run through, everything seems to work fine, and all the angles seem to reach pretty decently. However, if you do see this, without any joint constraints, without any of the angle constraints, my joints can kind of go everywhere, which isn't in the most realistic sense. Say for instance, this is a finger. A finger, the certain points are not going to be able to, a finger is not going to be able to do that. But in my implementation, I was able to do that more just fine. And that's my implementation of the pseudo inverse. All right, thanks.